Students, hi. Once again, this is session number 2. We are going to deal with a regular polygon inscribed in a circle. This is very new to you, students, so I hope that you are going to be very calm in reasoning, following me very closely so that you understand what I'm going to present to you. Regular polygon inscribed in a circle. What is this, by the way? So we'll start by defining what is it. A regular polygon inscribed in a circle is defined to be the regular polygon inside a circle such that its vertices touch the circumference of the circle. So actually, regular polygon, by the way, is any kind of shape with all sides equal in length. Any kind of shape with all sides equal in length. And this shape is always a loop, a closing figure. So a closing figure with 3 sides equal is called the equilateral triangle. 4-sided figure which are equal in length is called the square. If you move further forward, if it have 5 sides, we call it pentagon. Coming next is hexagon. Can you sing with me? I hope it will be after hexagon, heptagon, and so forth until you reach somewhere too many number of sides, but you are familiar to ending up when number of sides is 10. So that kind of shape we call it decagon. So no matter whether it is equilateral triangle, square, pentagon, hexagon, whatever, that kind of shape, if it is inside the circle such that vertices touch the circumference of the circle, so we call or we describe it to be a regular polygon inscribed in a circle. Diagram. So suppose this is the circle, and if you try to draw any regular polygon such that the vertices of the regular polygon touch this circle inside, so that regular polygon we describe to be a regular polygon inscribed in a circle. So here, maybe let us draw what kind of shape, which is regular. For me, let me draw a square. Okay, a square ABCD is inside the circle, and it happened that the vertices A, B, C, and D, all of them touch the circumference of the circle. This square is now called a regular square or a regular polygon which is inside the circle. To be inside, the necessary condition is that the vertices should touch the circumference of the circle. So I think with that sketch and with this definition, you can draw any kind of regular polygon inside a circle. It can be a pentagon. You can draw it. There's no problem. For example, this, call it sketch 1, call it sketch number 2. Maybe you can have a circle and you draw a pentagon. So we have five-sided shapes of equal lengths. One side, two, third, fourth, fifth. So this shape inside is pentagon, and if you see the vertices touch the circumference of the circle, therefore this one is called the regular pentagon inscribed in a circle. So you can draw any regular polygon inside the circle, no problem. You can draw hexagon, no problem. But I hope as number of sides become many, it will be practically difficult for you to draw. So, but for this, a square, pentagon, or maybe an equilateral triangle is easy for you to draw. That's no problem. Okay, this is our subtopic, which is very main for us. What is the main focus with this subtopic? The main focus is still there. Remember, our topic is about finding areas and perimeters of different two-dimensional figures. And one of the two-dimensional figures is regular polygon. But here we want to know how to find area and perimeter, given that the regular polygon is inscribed in a circle. So we are continuing with the lesson, students. As I said, the main focus with doing regular polygon inscribed in a circle, the main focus is to know how we can find perimeter and areas of that kind of shape which is being located in that manner inside the circle. So the main target is perimeter and area. Perimeter and areas. So for today, the session is going to only concern with perimeter. So let us put this one aside. We're going to cover this one in another session, but today's session is only finding the perimeters of a regular polygon inscribed in a circle. So we'll start with part A, which is perimeter. Of regular polygon inscribed in a circle. The good thing here is that I'm going to derive the formula that you are going to use to find the perimeter of one regular polygon inscribed in a circle. So you have to be calm because you are going to be governed by the formula. What is that kind of formula? So I'm going to derive here for you. Keep a close watch so that you understand every step in order for you to make sure that you can even derive yourself wherever you are. So students, in order to derive the formula, you have to consider or assume. So let's assume a regular polygon of n sides inscribed in a circle of radius r. Let's start with this assumption first. that assume you are having a regular polygon of how many sides? We cannot say it is 2 sides or 4 sides, 6 sides, but we are going to assume n sides because we don't know. So we assume that that regular polygon is either hexagon or is either pentagon, nonagon, decagon, whatever. But we are going to assume that maybe that regular polygon is having n sides. But we are going to inscribe that regular polygon using a circle whose radius also is not known. So we are going to assume the length of the radius to be r. Now sketch. Sorry. Sketch. So let's take the sketch of our assumption here. Okay, consider this sketch, students, that you have a circle, as I said, whose center is at this point. So a circle with the center there, and a regular polygon is inscribed here. Let's say the side is this one, and another side is that one, and another side is that one. So hopefully this can continue. So this side and this side's equal, that side's also equal. Call this center point O, and this vertex here, call it A. This again, call it B. Okay, if you join the line from O to A, this line is actually a radius. Why a radius? Because it is a line or distance measured from the center to the circumference. So this is defined to be radius. And again, OB will be the same. Radius. Dropping a perpendicular line from O, this line is called a perpendicular bisector. So it bisects the angle A or B, and also it bisects the line segment AB into 2 equal halves. So call this point here a point AB, so call it point C. Now this angle and this angle are equal. Even the segment here is equal to the segment there. So AC is equal to CB, also OA is equal to OB, and the angle AOC is also equal to angle BOC. Why? Because of this OC to be perpendicular bisector. Now from here we can try to extract some of the facts. So what we do is that the central angle which is A or B, by definition the central angle of a regular polygon inscribed in a circle is given by the total angle of the circle, which is 360, divided by how many sides that shape have. How many sides do regular polygon have? So if the regular polygon is having 5 number of sides, you put 5 there. If regular polygon is having 3 sides, you put 3 there, and you will get the central angle A or B. But because we don't know how many number of sides of that shape, because we assumed because we assumed that a regular polygon is having n sides, so we don't know for sure that this n is 5, 4, 6, 10, 100 or whatever. We are not sure, so we just have to put n as n. Now, so the central angle is going to be given as 360 degrees over n. But sorry for this marker pen. But the angle AOC is actually half of the angle AOB here. So you can see, because OC is perpendicular bisector, so this angle AOC is equal to half of the total. So if the total angle AOB is, for example, 60 degrees, that means AOC is going to have 30 degrees, half of 60. Now angle AOC is given by the half times the angle AOB. Okay, so here we have shown that the angle AOB is given by 360 degrees divided by n. So we have AOC is going to be equal to a half times angle AOB, which is this 360 degrees divided by n. So we'll times by 360 degrees divided by n. If you simplify 360 degrees divided by 2, you get 18 degrees over n. This will be the angle AOC first. This angle is very important for what we are going to derive. So keep in mind, keep attention to this angle. What we do next is to extract triangle But before that, sorry, there is another fact to share from this figure, that suppose AB is equal to S. Suppose the length from A to B is equal to S. That means even here also it will be equal to S. Even this side also will be equal to S. Why? Because these lengths, AB, this length and this length are the lengths of regular polygon. And remember, the lengths of regular polygon should be equal in length. So AB, the length will be S, here again S, and this again, this length is S. Now if AB is equal to S, this means that AC, check the side AC, AC is equal to half of total length AB. Are we going together? I hope so, that AB, AC is half of the total length AB, because this OC pass through the center, dividing line segment AB into two equal halves. So AC is half of the total AB. So this is a fact we can extract from this diagram. Okay, so AC equals to a half times S. Why S here, students? Remember AB, our assumption here is that AB is equal to S. So we plug the value of AB, and here AC is supposed to be half of S. Making subject S, this becomes S equals to twice times AC. This again is very important, so we want this and we're going to use this one in our proof or in our derivation. Okay, so let us see what is next until we arrive at the point that we want. So back to the diagram. Back to the diagram, students. Okay, so what next, students, is to extract the triangle OAC. So triangle, for triangle OAC, which is this one. Here is C, there O, here A. This one is 1, and this angle is 1/8/n. What you do, you introduce concept of trigonometry. So by trigonometry, the sine of angle 1/8°/n, this one will be equals to the opposite side, which is AC, divided by R. Making subject AC, you will get AC equals to R sine of 1/8° divided by n. So this one is the length of the portion A to C. The length of the portion A to C. But here the intention is to find the length of the portion A to B. Now, from AB equals to S, and we've seen AC is equal to a half S, which means S is equal to twice AC. So here now you plug the value of AC. We've found it. So if you substitute the value of AC, it will be twice. The value of AC we've found to be R, the sine of 1/8°/n. So if multiply, you get S equals to 2R sine of 1/8°/n. Now this one is the formula to find the side lengths of any regular polygon inscribed in a circle. We are trying to reach the end of this proof by doing this one. So if you want to find perimeter, it's now very easy, as long as you have this side of any regular polygon. In short, if equilateral triangle is having one side of the length 4 centimeter, that means the perimeter will be 4 plus 4 plus 4 centimeter. So in an alternative way, we can say it is 4 times 3. 4 times how many sides are there? So the perimeter of a square also, it will be 4 times a side given. The perimeter of regular pentagon also, it will be how many sides? 5 times any side length. Now, because we know that the regular polygon we've assumed here is having any sides, so we hope that perimeter to be given by n times the sides. So this side is now this one. So you can take the formula of S and plug back into this one, you'll get the perimeter. So it will be n times twice R sine of 1/8°/n. At the end of the day, you get perimeter equals to 2nr, the sine of 180 degrees over n. This now is the formula that we want, the formula that you can use to find the perimeter of any regular polygon inscribed in a circle of radius r. You can see the formula is depending on two factors. One of the factors is radius of the circle, and another factor is number of sides of that regular polygon. So you take this formula, and it's very useful to solve finding the perimeters of any regular polygon. But be careful, students. The regular polygon must be inscribed in a circle in order for this formula to be used or to be correct. If regular polygon is just alone, it is not inscribed in a circle, this formula is not useful. So it is only useful if the regular polygon is inscribed in a circle. So I hope you get this formula. You try to digest it. You can try to pass through the way we have proved it. If you find any question, please do not hesitate to ask me, and I will respond quickly. What next? We are going to check for examples. Okay, so now we have example number 1 to try to find the perimeter of a regular polygon which is inscribed in a circle. The question said that the perimeter of a regular hexagon, the perimeter of a regular hexagon inscribed in a circle of radius 10 centimeter. The main target is to find the perimeter of a regular hexagon which is inscribed in a circle whose radius is 10 centimeter. If you know the formula, calculation remains simple, students. Check this solution. Here you can break down your data that the shape given is regular hexagon. How many sides do regular hexagon have? How many sides? Actually, you'll find that the number of sides is equal to 6. But this one, you are given the radius. So the radius is equal to 10 centimeter. Now if you know the formula, calculation remains straight. Remember, the target is to find perimeter of this regular hexagon. So you have to know the formula. Introduce the formula, students, and solve. Okay, so we say from perimeter equals to twice nr, the sine of 180 degrees over n. Actually, you plug the information. N equals to 60 and r equals to 10 centimeter, then compute. Things will be over from there. So this one is 2 times n is 60 and r is 10 times the sine of 180 degrees over n. The value of n is 6 there. If multiply 2 times 6 times 10, this will be 12, and this one is 120. So we get 120 times the sine of 180 divided by 60. Hope you get 30 degrees. 30 degrees. The sine of 30 degrees, this is a special angle, the sine of special angle. So actually it's very simple that this becomes a half. So if you divide this one, you will get 60. Divide this one, you will get 60 centimeter. So here now you get the perimeter. Okay, example number 2, students. At least we are trying to do the second one so that you will understand how you can solve questions concerning regular polygon which is inscribed in a circle. This second example is to find the length of a side of a regular 12-sided polygon inscribed in a circle of radius 3 cm. So you collect your data. You find that the number of sides of a regular polygon is 12 sides, and the radius is equal to 3 cm. Radius is equal to 3 cm. So the first to find is the length of the sides. Length of the side is not a perimeter, it's just only one length. Not a perimeter, only one length. And after finding that length of a side, so it is also possible that you can find the perimeter. Okay, so from the formula, now because we are not finding the perimeter, so here we have to use the formula for finding the sides. Remember, we derived this one to be S equals to 2r, the sine of 180 degrees over n. So S will be equals to twice times radius, which is 3 cm, times the sine of 180 degrees over 12. Why 12? Because n given to be 12 sides. So simplify this one, you'll get 60 cm times the sine of 180 degrees divided by 12, you'll get 15 degrees. Use your mathematical table to read the sine of 15 degrees. Use your mathematical tables, and I hope after doing that you'll get the sine of 15 degrees to be 0.2588. Multiplying this one, these two numbers, you'll get 1.5528 centimeter. So what you need here is to approximate to 2 decimal places to make these numbers a little bit simple. So approximate, and we'll get 1.55 centimeter. 1.55 centimeter. So this is the length of a side of regular 12-sided polygon. This question is not saying to find the perimeter, but I can say hence find perimeter. So if the target is also to find the perimeter, we can continue finding perimeter so long as you have the value of S. It's very simple and quick. Let's check. So here what we do is say from perimeter equals to NS. So this will be 12 times 1.55 centimeter. At the end of the day, you get perimeter to be equals to 18.6 centimeter. Okay, so I think we have to end our session here. As you can see, some kind of raining is going to come. Thank you for your time and attention, students.